Welcome everyone to the Pipeline Reprocessing of JWC Imaging Data webinar. This webinar is going to give an overview of the JWC imaging pipeline and demonstrate how to process NIRCam and MIRI data from uncalibrated images to drizzled mosaics. The webinar is going to include examples on running the pipeline with custom settings and also show how to incorporate manual processing to address common imaging issues. So the session outline for today, first I'll give a brief pipeline overview. Then we'll switch over to Misty, who's going to show you how to actually run the pipeline in Python. And at the end, I'll show you an example NIRCam dataset that has several common imaging issues. And we'll go through a notebook that mixes the pipeline stages with some custom processing to fix those issues. So the imaging pipeline itself is divided up into three main stages. In stage 1, this is also called detector 1 pipeline in Python. This stage is going to apply detector level corrections to each group before ramp fitting. Stage 2 is going to apply additional instrument calibrations to create a fully calibrated single exposure. And then stage 3 is going to take several of those stage 2 products and drizzle them together into one final product. So for the stage 1 pipeline, your input is going to be an uncalibrated ramp in units of counts, and the output is going to be the rate.fits file in units of counts per second. The first step in stage 1 is a group scale step. This step is just modifying the, it's going to correct instances where the onboard frame averaging didn't result in the proper downlink values. The data quality initialization step is going to flag known bad pixels, or any of those that have known strange up the ramp behaviors, like the dead pixels shown here. The saturation step flags all pixels after a pixel becomes saturated and stops accumulating signal. Now, only for NIRCam, a super bias is subtracted to remove the fixed bias signal across the science pixels. So after this step, things like the picture frame effect you can see around the image here are going to be removed. Now, just for MIRI, the first few frames and the last frame are impacted by detector reset effects, and their behavior is different from the rest of the ramp. So for MIRI, the reset step is run on the first few frames to correct for these effects. But the very first frame and the very last frame are flagged entirely to avoid including them in the ramp fit, since these frames aren't able to be well corrected yet. The next step uses the reference pixels. This same step is run for MIRI, just farther down in their pipeline. These reference pixels are around the borders of your images. They're insensitive to light, but they are sensitive to the various signals imposed by the readout electronics. So the reference pixels are used to correct for those effects in the science pixels. Some of those effects include the signal levels imposed by the different amplifiers, the horizontal striping called 1/f noise, as well as things like the odd-even column effect, which is an effect in NIRCam where alternating columns have different overall signal levels. After that, the linearity step is run. This step is going to correct the nonlinearity seen as signal accumulates up the ramp. And now for only integrations after the first integration, MIRI is going to run a reset switch charge decay step. This is going to flag the first groups in those integrations as bad since the various reset effects haven't decayed away after only the single reset that occurs between integrations. After that, the dark current is subtracted. This is the signal that accumulates even when the detector is not being exposed to anything. This is also the step that's going to correct hot pixels in the images. Next up is the jump step. The jump step identifies cosmic ray hits that occur during an exposure and flags them in the corresponding group's data quality array to avoid including their values in the ramp fit. So in this example pixel here, you can see a cutout of the same region for 4 groups up the ramp. And in that last group there, you can see that central pixel gets hit by a 2000 count cosmic ray, and it's flagged in the corresponding group's data quality array there at the bottom. So that's all this step is doing. And then the final step for stage 1 is the ramp fit. This step performs a linear fit to all of the calibrated good groups and records that slope value in counts per second in the rate image. So sticking with this example, for this pixel, that last group got flagged. So it's going to fit those first 3 groups, which as you can see in the rate image here, results in a very low slope value. So next up is the stage 2 pipeline. This pipeline is going to take the output of the stage 1, which are those rate.fits files, and the output of the pipeline is going to be a cal.fits file in surface brightness units. First step in stage 2 is the background step. This is going to subtract the background from any of your background exposures from your target exposure. Assign WCS creates an extension in the data to transform between pixel coordinates and world coordinates. The flat field step is going to correct the varying pixel sensitivities across the detector. For example, as you can see here, NIRCam has some strong cross-hatching regions with lower sensitivities. After that is the photom step. This is the step that multiplies a scalar value onto the data to convert from counts per seconds to megajanskis per steradian. A pixel area map is also going to be appended to the data in this step. And now the output of the photom step is going to be the final cal.bits file we'll use in stage 3. However, there is one more step run called resample, and this step just creates an undistorted version of each cal file, but it's not actually used for the rest of the pipeline. It's just useful in some other applications. So finally, stage 3, this is the stage that's going to take several of those cal.bits files. So for example, all of those in your dither pattern, and it'll combine them all together and do one single undistorted image. Those will have the i2d.bits suffix. So the first step in stage 3 for imaging is tweakreg. Tweakreg is going to find the centroids of point-like sources in each image. It's then going to compare those values across the different images and apply shifts to their world coordinate system information to better align all of those images in WCS space. SkyMatch calculates the sky values in each image. By default, these aren't subtracted here, but the values are used further down the pipeline for the image combination. Next up is the outlier detection step. This is going to identify outliers between the images in WCS space. So this step is useful to catch any remaining bad pixels that either weren't corrected or were not flagged in the previous steps, just to make sure they don't show up in your final image. And then the main step here is resample. This is the one that's actually going to take all of those images and combine them into one undistorted image. And then finally, the source catalog step creates a catalog containing a variety of photometric information for each source in that final image.